Okay, so recording. All right. So last time we talked about the renormalization group flow diagram, at least in conceptual terms, and we talked about critical fixed points. We talked about relevant and irrelevant directions. I showed you without demonstration what the flow diagram would look like for an Ising type system, a system with nearest neighbor interactions, but also next nearest neighbor interactions. We talked about the idea that there's a critical manifold, and that critical manifold has on it the critical points of all systems in that universality class. So if we look on the left-hand screen, in the left-hand screen there we have a subset of this. So remember, a manifold is a subspace. So if I think about the space as being two-dimensional, meaning the nearest neighbor coupling constant K1 and the next nearest neighbor coupling constant K2, then you can see that there are 2 points. There's a critical fixed point for the Ising model, which is K1 star. There's a critical point for the next nearest neighbor Ising model, which is K2. They both flow into the same critical fixed point in the middle there in a square box. That square box is the critical fixed point on the critical manifold. The critical manifold is the line indicated in blue, and that every point on that, as we said, flows into that critical manifold. And we can see that the nearest neighbor Ising model and the next nearest neighbor Ising model have the same universality class because they flow into the same critical fixed point, and the relevant directions of that critical fixed point are the same, therefore, for both of them. And so that's why they have universal, why even the behavior away from criticality is universal. We also saw that the fixed points at 0 and infinity tell you about the phases of the system. So on the lower axis, if we just ignored the next nearest neighbor coupling constants, then you see a flow which goes from the critical fixed point to the right and to the left. And the right fixed point is K1 is equal to infinity, which corresponds to the coupling constant J is infinity. And therefore, that means the system is fully, very, very strongly ferromagnetic. So that fixed point tells you about the ferromagnetic phase. And every point with K greater than the critical K1 star flows to that fixed point. Since K1 star is J over KT, then having been K greater than that means that T is less than TC. And so every system with T less than TC will flow towards the same fixed point, which describes the ferromagnetic phase. Similarly, if I go to the left of the critical fixed point, K1, if I go to the left of it over here, then I flow towards a fixed point at 0 K1, which means T is equal to infinity, or if you like, equivalently, J1 is equal to 0. And that then means that we have no effective interaction between the nearest neighbor spins, and so we have a paramagnet. So we can deduce the phase diagram just from the flows and where you go to. We talked about the relevant directions. The relevant directions push you away from the critical fixed point. And since the relevant directions push you away from the fixed point, that means that if you want to get to the critical point, you have to attune the variables that correspond to the relevant variables so that they are 0. Otherwise, if they're not 0, then you get pushed away. So the relevant directions correspond to the variables that you need to tune to have some specific value in order to be at the critical point. So let me just summarize that. So you have to so summary from last time. The relevant directions push the flows away from the critical fixed point, So if you want to be, if you want to get to criticality, and thus be on the critical manifold, you have to adjust your coupling constants, K, to have zero components in the relevant directions. And so what that means is that the number of relevant directions is equal to the number of variables you have to adjust in the lab to get your system to be at criticality. Now, here's a very important point that people forget about a lot. And that is, people talk about, oh, there's relevant variables and relevant things, and they use relevant and irrelevant. And they use these terms as if they have meaning on their own, but they don't. When we talk about things being relevant or irrelevant, it's always associated with a specific fixed point. So you have to specify that. You can't just say, oh, so-and-so is a relevant operator. You have to say, so-and-so is a relevant operator at the Gaussian fixed point. So-and-so is a relevant operator at the diffusion equation fixed point. So-and-so is a relevant operator at the Euler equation in fluid mechanics, or whatever is the problem that you're talking about. So you have to say relevant associated with a specific fixed point. And then what I showed you just and we discussed is that the phases of the system, in other words, the phase diagram, can be read off from the flows. And and then the origin of universality, the real origin of universality, is that both the nearest neighbor Ising and next nearest neighbor Ising, they flow to the same critical fixed point, and then they have the same relevant directions because they're at the same critical fixed point and therefore the same critical exponents. And then if I want to read off the phases of the system are sinks. So in other words, in the example that I showed you last time, if I have K1 and K2 are both equal to 0, so that is one of the sinks, and that means that J goes to 0 or T goes to infinity, and that means this means here a paramagnet with no nearest neighbor or next nearest neighbor spin interactions. And if I think about the other interpretation, t going to infinity, that basically means that entropy is more important than energy, because F is equal to U minus TS, and therefore the entropic fluctuations beat the ordering. And then the other phase diagram, the other fixed point was K1 equals K2 equals infinity, and so that means that J KT goes to infinity. And when I say J here, I want to emphasize I mean both of them. So think of J1 and J2. Think of J1 and J2, the nearest neighbor and next nearest neighbor, they both go to infinity. And so what that means, I interpret this, this means that either J1, J2 goes to infinity, implies huge spin interactions, and that will tend to order the system because they try to minimize the spin interactions. And on the other hand, if I think about the t going to zero behavior, so this is t going to zero, then the energetics dominate over the entropic fluctuations. So this renormalization group picture is a very different interpretation of what we already knew and learned from On Your Mother's Knee about energy and entropy competing at phase transitions. So there's a corollary of this, which I want to briefly mention. I'm not going to go into it in detail, but it's described in my book. So the corollary is, let's think about the Ising model. So you might say, well, why don't we say that that YT is associated with a variable T and YH is associated with a variable H. Now, it's not really true. As we'll see, the variables that we have as relevant variables may be linear combinations of the physical variables that you tune in the lab. But for now, let's just be simplistic and let's make that direct association, even though it's not completely true. Now, I want to explain how we learn something else about the behavior of the phase diagram. So then the question is, how can we predict the order of phase transitions? And how does that emerge in this picture? So I'm going to just tell you the answer. I'm not going to go into the mathematical detail, but let me just explain to you, to show you that it is something that is also explained by this formalism. So let me draw my phase diagram for an Ising magnet, and that phase diagram looks like that. We have the HT plane. This is the origin. There is a cut along here, and then this is TC. And what we know from everything we've done previously is that this transition going through here at H equals 0 is a second order transition. And this transition going across here is a first order phase transition. So, at this fixed point over here, what we expect is we have to tune h equal to 0 and t equals to tc. So that's therefore implies two relevant variables, which is correct. If I look at the fixed point associated with t less than tc. So from what I told you before, if I were to start with my system at some temperature t less than tc, just shown over here, then if I coarse grain and do normalization group transformations, I will eventually flow down to a fixed point over here. So the flow that I'm drawing the renormalization group flow on my physical phase diagram, but I hope it's clear to you what I mean by that. So this fixed point here, this is the ferromagnetic fixed point that we talked about before. So that fixed point associated with t less than tc, that fixed point has special properties. And the what I want to mention is that if I look at the critical exponent, if I look at the eigenvalue YH associated with that fixed point in the H direction, then that is equal to D, where D is the dimensionality of the system. And that and if this is true, this condition can be shown to imply that you have what's called a discontinuity fixed point, which is a signature of a first order transition. Okay, so that is shown in my book, and it's not hard to do the calculation, but I'm not going to do it in class. Okay, so now I want to just to summarize what I've just told you. So basically, the bottom line here is that the renormalization group picture derives the assumptions made in an ad hoc way by Kadanoff, but they do more than that. And so now let me explain what the extra thing is that it does. So let me give you an example. And my example that I'm going to do is I'm going to just choose a one relevant variable fictitious example. So if you go back and we look at our flow diagram over here on the left screen, there I've drawn two dimensions, K1 and K2. You probably realize that there's a third dimension. What's the third dimension that's not drawn on that? H, that's right. H is also missing from that. And then you could say, well, what about the next nearest neighbor, K3, and so on and so forth. So in principle, all of those things can be there. I've just drawn for you a subset of that. Okay, let's have a look at just the one-dimensional axis, the K1 axis. Okay, so let's just look at that flow. So we're going to look at the one relevant variable case, i.e. the K1 axis in my previous picture. And if you just look at that and you don't know about the K2 and the H and so on, you just think that that is the whole universe. It's not true, but it's the whole universe. Let's ask ourselves the following question. What is the critical manifold for this one-dimensional renormalization group flow? So here's my one-dimensional renormalization group flow. The variable it looks like this. There is TC, and the flow looks like that. Where on this picture is the critical manifold?
Zero.
Nope. It's the point of TC. That's correct. The critical manifold is now here. Why? Well, when we talk about the manifold, it has to be a subspace. The space here is just one-dimensional. It's just a line. So if you're going to be a subspace of a line, then you have to be a point. And so you just have that one point. And of course, you sit it there, you're at criticality, and it's a fixed point. When you go into the two-dimensional space that is shown on the left-hand panel, then you see that that point that we're calling the critical manifold here, I'm going to put a little quotations around it. That critical manifold there is actually part of a much bigger, more general critical manifold, which is the one indicated on the left-hand panel. Okay, so let's have a look at what would happen if we did renormalization group in just one variable. It's just a fictitious thing. You would never really do this in practice, but let's just look and see what happens. So in this, if we had one relevant variable, then I could say that what the renormalization group does is it takes the system at temperature T and maps it into a system at temperature T prime. Okay, so coarse graining moves you away from TC. We already saw that with Kazanoff's picture. So I can think of it like that. And then what I'm supposed to do is I'm supposed to linearize that picture. So now I linearize that. When I linearize, then I get that T star is equal to RL of T star. So therefore, T prime minus T star is equal to RL of T minus RL of T star. So this is my fixed point condition. This is my a deviation from the fixed point, and then I'm going to linearize. So I'm going to write, I'm going to expand RL of T is equal to RL of T star plus T minus T star times derivative with respect to T evaluated at T star. So that's what I'm supposed to do. And I'm going to call this variable, I'm going to call this lambda sub L, and lambda sub L, just to write it out fully, dRL by dt evaluated at T star. Now remember that we use the semigroup property to prove that lambda of L must have the form L to the y sub t. So that's how we derived that last time. That was assumed by Kazanoff, but now we've derived it. And if we are initially at some, let's say, temperature greater than Tc, then I can write T is equal to T minus T star over T star, and T star is in this case equal to Tc, and therefore I get T prime is equal to T times L to the power y sub t. And then I iterate this n times, iterate my linear Rg n times. So then I get T, the nth iterate, is equal to T times L to the power y sub t, raised now to the nth power like that. So that's what happens when I do my iteration. And if I then compute the correlation length, and I get that psi of t is equal to L to the n psi of t of n. Every time I coarse grain, the correlation length changes by a factor of L, and then L to the psi of t of n is psi then of t L to the power n times y sub t after n iterations. And then the usual thing in the normalization group is I'm going to choose L to the n in such a way that it is equal to some number of order unity, which I'll call b, over t raised to the power 1 over y sub t. There's nothing to stop me doing that, where b is some number of order unity. And then what I've just learned from this is then this implies that psi of t is equal to b to the minus 1 times t to the power minus 1 over y sub t times the correlation length evaluated at little t equals b. And that's just a number of order unity, and this is true as t goes to 0. Okay, so that you've seen this equation now quite a few times, and you might be getting bored with it. And you could say, well, first of all, what is b? So, well, I can say, well, b is such that if I take L to the n, that equals some integer. So that gives me some value for b, and that's going to be a number which implies that psi of b is far away from T equals Tc. So that's just a value in the high temperature phase. So this might be small, maybe a few angstroms, and it's in a regime far from the critical point where, for example, perturbation theory works. So I can calculate that number, and then the other thing that I know is that we know that psi of t then is going as psi of b times t to the minus 1 over y sub t, but we know this has to equal the correlation length well away from Tc times t to the minus nu, and so we read off that nu is equal to 1 over y sub t. So far, you've seen this before. We did exactly these manipulations when we did the Kadanoff block spin construction. But there is one big difference. And that big difference from Kadanoff's picture is that we know that if you look now on the left-hand screen, we know that lambda sub L is equal to drL by dt, and we know from the semigroup property that lambda of L is equal to L to the y sub t. And so that means, what that means is, we know how to calculate y sub t. It's not just some random number. If I've got a normalization group transformation, it's just a nonlinear function, and then I can do the differentiation and calculate what yt is. And so I've calculated yt, and therefore I've calculated the critical exponent nu. And so we know how to calculate yt because we know from the linear RG transformation. That's the big difference. That's the big difference. It's not just hand waving. We actually know how to calculate it. So that's example that's example number one. Let's call this here on the left-hand side. Let me call this example number one. And then here on the right-hand side, what I want to do now is a second example. I want to show you what happens when I compute the renormalization group for the free energy. More specifically, the free energy per spin or the free energy density. So we already saw that the free energy, the singular part of the free energy, scales like this, L to the minus D times F of T prime, where T prime is the image of T under a specific renormalization group transformation. So we'll do the same thing as we did before. We just do N iterations, choose L as before, and then what I end up then with is the equation F of T is equal to T over B to the power D over Y sub T times F of B. Okay, so just quickly to make sure you can all see what happened there. So what happened was I chose L to be a specific value. Because I chose L to be a specific value, then it comes in here, and the specific value of L that I chose is the one that is over on the left hand, is on the left hand side. Over here, just pointing it out on the left-hand side. And so that's how the T dependence comes in front of the F. F then is evaluated at a distance B, where T minus TC is some order one, so it might be at twice TC, somewhere way above the critical temperature, where I can just calculate it by standard methods. And so I've now seen how the free energy scales. And then if I then say, well, if I want the heat capacity, so C is basically twice the derivative of the free energy. So therefore, and we know that C scales as T to the minus alpha. And so that tells me then that differentiating twice gives me D over Y sub T is equal to 2 minus alpha. And I've just shown you that 1 over Y sub T is equal to nu. So that means then that D times nu is equal to 2 minus alpha. Oops, sorry, 2 minus alpha. And that is the scaling law due to Josephson. But now it's better than Josephson's scaling law because this thing I calculated. Because it's just 1 over Y sub T, and I calculated Y sub T because it's the exponent describing the eigenvalue, the relevant eigenvalue from the linearized renormalization group transformation. And so now I've got nu calculated, and that means I've now calculated alpha. And so I get everything like that. So this in a nutshell is the processing pipeline, if you will, for a renormalization group. All right. So now I want to move on and talk about the differential renormalization group very briefly. So this is in section 9.5 in my book, the differential renormalization group. And what is the idea here? Well, the goal of this is the following: doing discrete iterative maps, like we've been talking about up to now, is not that convenient. What we actually like to do is calculus. And so what we want to do is have a continuous description. And that means that we go from discrete maps to ordinary differential equations. So usually in the past, we use ordinary differential equations to describe dynamical systems. And what people did in the 1970s was people realized that if you want to understand chaotic systems, actually you take the differential equations and map those into discrete maps. Those are like the Poincaré return maps. That was the idea of looking at systems and snapshots and then looking at the maps of those. That was ended up producing what's known as the period doubling route to chaos, which one of my friends, Mitchell Feigenbaum, is famous for discovering and using the normalization group to understand the transition to chaotic systems. But now we're going to do the opposite. The normalization group is explicitly a discrete set of transformations, and now we're going to run it into the continuum because it's going to be more convenient. So it's conceptually really trivial. So let me just quickly rush through the general idea. So we start off with a lattice with spacing, just call it A. Then we do a RG transformation to get blocks of size LA, like L could be 3 or something like that. And then what we're going to do, you saw already that we kind of already do this. We kind of think of L as being a continuous variable. We chose L to be such a variable that after n iterations, we're far away from the renormalization group fixed point. So what we're going to do is then we then say, and now construct blocks of size S times LA, where 1 is less than or equal to S is less than infinity. And so that makes it into a continuum. And then we're going to make S equal 1 plus epsilon. And that way we can make it continuous. So let me show you what one gets when one simply does that in equations. So we start off with our renormalization group transformation from K prime is equal to RL on K. So that's where we start with. Now we go to L, to scale L, and then we go to a further scale S times L. So what that means is if I compute the image of the coupling constants at the scale S times L, that is equal to the renormalization group transformation at scale S acting on the coupling constants at scale L. And so then I can define d of KL by dl. So that's the derivative. That's defined as the limit as epsilon goes to 0 of the coupling constants at the scale 1 plus epsilon times L minus the coupling constants on the scale L divided by L times epsilon. So I've just made S equal to 1 plus epsilon. And then what that equation then tells me is that 1 over L dRs by ds of KL is a quantity that I'm going to define to be 1 over L B of KL. This I evaluated at S is equal to L. And so then in these units, then what I get is d by d tau of the coupling constants on scale tau is equal to B on the scale of K tau, this quantity, and this and in this, because I've got this 1 over L in here, then this tau is equal to the logarithm of L. And so this this is literally an equation of a dynamical system in a fake time. Tau equals the logarithm of L, and this function here, this function over here has a name. This is basically known as the beta function, and it tells you how coupling constants change continually with scale. And if I want to know what the fixed points of the system are, well, the fixed points of the system are defined by B of K star is equal to 0, and that gives you the fixed points. So this is useful. This is really useful because I can take a very complicated system. It can be equilibrium, like magnets. It can be non-equilibrium, like the KPZ equation for looking at interfaces, or the equations for fluctuating hydrodynamics, or the equations for machine learning in neuroscience and so on, or AI and neuroscience. All of those things behave can be formulated, their renormalization groups can be put into these continual forms where you have just ordinary differential equations, a system of them, and then you can just do the usual tricks of simple dynamical systems, differential equations in order to do the analysis. And I've spent time on this because many of you are going to be reading papers for your term essays, and you will undoubtedly come across the renormalization group formulated in this way. And so now you know what's going on here. Okay, now we've talked about the development of the theory, and I think it's really great, but it's time to actually do an honest calculation. So I'm going to do an honest calculation for you now. And so what we're going to do is take this, hopefully not delete it, copy it, and then put it over here. Yay, it worked. Okay. All right. And then I'm going to go back to here. So what we're going to do now is I want to do section 9.6 in my book, which is the renormalization group for the 2D Ising model. So now we're done with all the abstract theory. Okay, so now I'm going to show you how we can really do this calculation in practice. So what is our goal? Our goal is to do what's called a real space, RG, on the Ising model, and I'm going to do it on a triangular lattice. Now, normally you say, well, why are you doing that? You know, why don't we just use a square lattice? Like it's much easier. The reason is this: it's super easy to define the coarse graining on a triangular lattice. You may not think so, but it is. It's super easy, and you don't have to do things like choose L to be an odd number and things like this. So this is the idea, and what we're going to do is we are going to see that here's my underlying spins, and then I'm going to group these block spins together. That's a really terrible choice of color. I'm going to take these block spins. So here's 1, here's 2, and here's 3, and we're going to put them together, and then we're going to see that the block spins, when they're going to interact with each other in that way. And you can see in the blue triangle shows you what is the coarse-grained lattice. So I'm starting off with the lattice that's shown in the picture, and I'm going to define my block spins to be the shaded ones, the ones outlined in red. And then once I've done that coarse graining, those block spins are now going to interact. They're going to be on another triangular lattice, but it's going to be triangular lattice rotated by 60 degrees, and it's the blue lattice. And you can see that the blue lattice has got a bigger lattice spacing than the original black lattice does. So that is the picture we're going to do. So now let's go ahead with the calculation. So the Hamiltonian for the system is the coupling constant K times Ij, nearest neighbors, Si, Sj, plus H times sum over spins, Si. And I'm going to define my block spins. So those are the ones that I've shown you in the picture, and those are defined to be just the sign of S1I plus S2I plus S3I. Okay, so let's just check in to see what I mean by that. So look at those block spins. Let me make a big picture of those block spins. So here is one of the block spins. This is block spin I, and that is that's the shaded thing in the picture from my book. And then I can label the spins here. These are the microscopic spins that make up the block spin. So this is S1, this is S2, and this is S3. So those are the microscopic spins that live in the block spin. And we can do some simple geometry. So we can ask ourselves, well, the block spin lattice, which is in blue on the picture, that block spin lattice is enlarged from the original lattice by a factor. Well, you can just do the trigonometry. It's L equals the square root of 3. Okay. And then the other thing is, because of the way I've defined my block spin, notice that SI is always plus or minus 1. Okay. So what are we going to do now? So what I want to do is I want to calculate the critical behavior, and we're going to compute the critical behavior and we're going to compare with what? We're going to compare with Onsager's exact calculation. So it's not very often that you can do this. Only very special systems where you can start off with a partition function and just grind away and eventually do the whole calculation explicitly. It's very, very hard. As I've told you before, Onsager was a real genius in being able to figure that out in 1944. And we have that calculation. You can't do it in 3 dimensions. You can't do it in the Ising model in 2 dimensions with an external magnetic field. You can only do it for the 2D Ising model in 0 external field. There's other systems which you can do it for, various special models in statistical mechanics, and those special models have very special mathematical features that enable you to do the calculation. And those special features then are related to certain types of partial differential equation, Pain-Levi equations. They're related to various group theory constructions, what are so-called Virasoro algebras in string theory, that the whole basis of string theory and conformal field theory came from these exactly solvable models. So you might say, why do we need renormalization group at all? We can just use these techniques from Onsager and solve these problems exactly. Well, you can only do that in special cases. Even Onsager couldn't solve the 3D Ising model. Even Onsager couldn't solve the 2D Ising model with an external magnetic field. We want to have a tool that is guaranteed to work in any situation. So straightforward, so easy to use that even a physicist can do it. Okay, so that's what we're going to do now. So what is the specific strategy? Well, what I'm going to do is I'm going to compare with Onzaga's exact calculation. And what did Onzaga actually prove? So let me just give you some of the critical exponents. So what he did was he did 2D. He set the external field equal to 0, and he was able to compute that alpha is equal to 0, delta is equal to 15, and eta is equal to 1/4. And these results are exact. Delta, remember, was the breakdown of linear response theory. And eta is the critical exponent for the correlation function at t equals tc. So he computed all the exponents. You can get everything from Onzaga, but we're just going to look at those ones. And here's what we're going to do. The way I'm going to do this is the following. We're going to work backwards from Onzaga's answer, and we're going to compute what should be the exact result for the renormalization group eigenvalues. So what I'm going to do is say, let's suppose we've done Onzaga. What if I could do the renormalization group and the renormalization group was exact and worked? What would the values be for the renormalization group transformation eigenvalues? So I'm going to work those out. And then we're going to work them out in a simplification in this simple RG transformation that I've defined and see how close they get. So the strategy is going to be step one, use Onzaga to get the exact results for the renormalization group eigenvalues. So we're going to work backwards from the answer. And then step two, I'm going to calculate the RG eigenvalues in an approximate scheme using our real space renormalization group transformation. So that's the process that we're going to do. So let's go ahead and do the easy part. So let's do step one. So step one says work backwards from the known values. So we know that 2 minus alpha is equal to nu times d. We know that d is equal to 2 and alpha is equal to 0. Alpha equals 0, by the way. You may wonder, what does that mean? There's no power law divergence of the heat capacity. There isn't. It's a logarithmic divergence of the heat capacity. So he calculated that, but a logarithmic divergence, you think of it as being an exponent that corresponds to an exponent equal to 0. That's yeah. If you don't know why that is, I'll tell you afterwards. Okay. So this alpha equals 0. What it's meaning is that the heat capacity diverges as a logarithm of T minus Tc over Tc, something like that. I think it's the logarithm to some power. I've forgotten, but something like that. Okay, so that means, therefore, that in this calculation, then nu should be equal to 1. And that means, since yt is 1 over nu, that means that yt is equal to 1. Okay, if yt is equal to 1, I know that lambda t, the renormalization group eigenvalue in the t direction, that goes as L to the power y sub t, and y sub t is equal to 1, So this is L. And what is the scale of L? Well, we calculated that from the picture. L is equal to √3. So what that means is that if we did this calculation precisely, we would get that the normalization group eigenvalue in the temperature direction should have the value of the square root of 3. Okay, so that's yt, but we know there's another eigenvalue, which is y is lambda h. So to get lambda h, I'm going to use another scaling relation, which I derived a couple of lectures ago, and that was this one. It's 2d minus yh is equal to d minus 2 plus eta. I derived that because I showed you how to do the coarse graining for the correlation function at Tc. And so that means that yh is equal to d plus 2 minus eta divided by 2. And then if I plug in the numbers, that means I get 15 over 8. And so then if I want to compute what lambda h is, then that says that lambda h is L to the power y sub h, which means it's square root of 3, all raised to the power 15 over 8. And that, if you do it, is something like 2.80 ... Okay. So the thing I want you to note is that lambda t and lambda h, as you can see here, explicitly depend on L. And therefore, in other words, they depend on the renormalization group transformation. So that's fine, but there's nothing wrong with that. The exponents are independent of L. Okay, so that's step one. Now let's do step two. Step two is the interesting part. So what we're going to do now is we're going to coarse grain explicitly. So now I need to go through that fairly carefully. So let's take I'm going to define sigma I. By that I'm going to mean all the spins that are in a block I. So that would be S1 I, S2 I, S3 I. So this is all the spins, the microscopic spins in the block I. So I'm just going to use the notation sigma to denote them, otherwise the writing just gets too complicated. And then the block spin variable, and then what I want to do is I want to enumerate the configurations of sigma I corresponding to the two values of the block spin Si. So let's go ahead and just enumerate what those are. So what I'm going to do over here is I'm going to say, here's Si, I've got a block, and I know that the block spin has values +1. What are the microscopic configurations that correspond to that? So we can easily write them out. So those sets look like this. So there's one where two spins are pointing up and one is pointing down. I can have another one where I have this and then this and then this. So the down one is over there. Then I can have the down one over here and then the two up here. So those are the configurations that correspond to the block spin pointing up. There's one configuration that I missed. What is it? Go ahead. Do you know? They're all pointing up. Yeah. You are Jiwan. Jian? No. No, Jinting? Jinting. Okay, thank you. All right, so we missed another one, which is all the spins. Thank you very much, Jinting. So we missed this configuration. So there's 4 of those. If on the other hand, I say, well, let's look at SI is equal to -1, then the possible values for the microscopic spins, well, it's obviously just reversed. So it's got 2 down, and then 1 up, and then 1 up, 2 down, then 1 up, 2 down, and then 3 down. So those are all the configurations. And let's just check. Let's just do a check. Do we have the right number of degrees of freedom? So let's do a quick check. Have we preserved the right number of degrees of freedom? So let's have a look at the microscopic scale. So the microscopic, I've got 3 spins. Each can be in 2 states. And so that means that I have 2 cubed equals 8 possible configurations. On the other hand, at the macroscopic scale, on the macroscopic scale, I have 2 block spins, 2 block spin values. SI is plus or minus 1. I have 4 corresponding microscopic configurations which are consistent with each block spin value. And so therefore, what I have then is 2 times 4 equals 8 configurations. So that's good. I didn't miss anything. As we've talked about before, when you're coarse graining and when you're doing the normalization group, you're just summing over the degrees of freedom in a different order and in a different way. Okay, so that's the first thing. And what's the next step? Well, the next step is to calculate the effective Hamiltonian. So remember how that is defined. So what we say is, well, my effective Hamiltonian is called e to the h prime. It's going to depend on the coarse-grained, the block spin variables s sub I, like that. And how do I get that? Well, what I do is I start off with my microscopic Hamiltonian, but now written as a function of SI, the block spin, and the microscopic degrees of freedom, which I'm calling the sigmas. That's just the sub spins inside each block spin. And then what I'm supposed to do is I'm supposed to do a trace over the block, over the microscopic configurations for each block spin. So here what I'm doing is, by writing it like this, what I'm doing is I'm integrating out the microscopic degrees of freedom and I use the phrase integrating out the microscopic degrees of freedom because in general this would be in continuum, it would be a field theory, so you call it an integration, but a summation is just the same as an integration. Okay, so we're going to do that, and then this thing over here, this is the effective Hamiltonian. So you tell me what is SI. I put that value of SI into here, and then I do the sum over the sigmas. So these sigmas over here and summed over here, these are the dummy variables. And once I've done that sum, I now have left some quantity, which I'm calling e to the h prime, which will now just depend on the block spin variables. So this equation actually defines the effective Hamiltonian h prime. Okay, and the point is, once I do that, then I can then read off the renormalization group recursion relations or the coupling constants. And so we're going to do this specific calculation. So this thing here, we're going to do specifically in an approximation scheme. And what is that approximation scheme? It's a form of perturbation theory. It's called a cumulant expansion. So it's a cumulant expansion in perturbation theory. And I'm going to show you how we do that now. So let me show you how we do it. And usually when I just wanted to say something here. When I talk about perturbation theory basically just means I've got e to the x. I just write it as 1 plus x squared over 2 factorial, blah, blah, blah. That's what perturbation theory usually means. You just expand e to the x. Okay, so if you've got a partition function, e to the kinetic energy plus potential energy, you can expand it e to the x using perturbation theory. Okay, the cumulant expansion is not that. It's a different expansion. It's a better expansion. And I'm going to show you what it is in a few minutes. Okay, and I'll define it for you very carefully. Okay, so that's what we're going to do. And then the next thing we're going to do is we're going to set now the external field equal to 0, and then later we will remove this restriction. Okay, so what is the basic idea here? So the basic idea is I'm going to write the Hamiltonian as being in this way. First of all, there's going to be interactions within a block and then there's going to be interactions between blocks. Okay, so that's the trick that we want to do. Now the original Hamiltonian isn't written down in terms of blocks, and so it doesn't have that form. So we're now going to beat it down into this form. So let's see how we do that. So that means I'm going to write Hamiltonian as some h naught, which is the interactions within blocks, plus v, so this is within a block, plus v, which is interactions between blocks. So that's the idea. And what is the form of these things? Well, we can easily write down what h naught is. It's just k times the sum over the blocks, and then I'm going to sum over the spins I and j, which are inside the block I, and then Si, Sj, like that. So that's for every block. I just go through each block and I look at the interactions between the spins within each block. Then the interactions between blocks, I'm going to write it down, and in a minute I'm going to draw you a picture and show you where this comes from. So the interactions between blocks looks like this. I've got the coupling constant, then I have the sum over block spins I and block spins j, but they are different block spins. Then I'm going to sum over I in block spin I, little j in block spin j, and then Si, Sj. So that is my picture. Let me draw this for you now in cartoon way. So here is block spin I, and then here is block spin j. They're on this triangular lattice. Remember the triangular lattice that we drew a few pages back? Here, there's the picture over here. So what I've drawn you here is just like a subset of the picture on the left. Gregory, you have a question?
Yeah, so just wanted to make sure we assume nearest neighbor interaction.
Yes, nearest neighbor Ising model.
Okay.
Okay, nearest neighbor Ising model. Okay, to start with. Okay, so here's my picture. So we're just looking at, if you think of this picture over here, what I've drawn here is this thing here. Okay? I just drawn it. Okay, so let's label the spins. So this is spin 1, spin 2, and spin 3. This is spin 1, spin 2, and spin 3, but they're on different blocks. So if I want to know what are the H naught, that would be this sort of interaction. And if I want to know what is the V, that would be this interaction. Okay. So we're going to treat that H naught is our unperturbed Hamiltonian. And V is our perturbed Hamiltonian. Okay, so now comes the cumulative expansion. Whoops, don't want to do that. Not quite yet. So what we want to compute then over here, if you look on the left page, you can see that what we're doing is a sum over the microscopic degrees of freedom of e to the h. So the thing that we're going to want to calculate is something like e to the h evaluated with respect to our unperturbed Hamiltonian. And so this means with respect to that h. So that's what I'm going to mean by those angle brackets. So let's look at this a little bit more closely. So let's suppose I have some object that depends on my microscopic spins, and I want to compute its expectation value with our unperturbed Hamiltonian. So what I mean by that is that this thing is defined to be the following: e to the h naught, and h naught now depends on the block spins and the microscopic spins. Then I have the quantity A that will now depend on the block spins and the microscopic spins. And then I'm going to sum over the microscopic spins. And then I'm going to normalize it at the bottom by the partition function. And the partition function is just the sum over sigma e to the h naught of the Si and the sigmas. Okay, so that is if I assume that there were no interactions between the blocks, then any expectation value of any quantity would simply be take the probability distribution, which is the Boltzmann factor e to the h naught, divided by the partition function, which is e to the h naught. Okay. So that's what that's the definition of that. Okay. Now we want to compute e to the h prime of Si, and that, as we saw, is the sum over the sigma i's of e to the h, and it's the e to the h naught plus v, like that. And so I can write this as the sum over the si's of e to the h naught of si sigma I, and then the expectation value of e to the v with respect to this variable here. So treating this as a perturbation, then I have to compute the expectation value of e to the v. Okay, so I'm not going to finish this today. Let me go a little bit further and then we'll stop. So let's suppose we have m blocks in the system. And what that means is that the sum over sigma I e to the h naught of si, like that, that is going to be just the sum of the spins inside each block. So it's going to be the partition function of one block. I'll call that as z naught of k raised to the nth power, because we're perturbing in the interaction between the blocks. So when the blocks are not interacting, I've got a block here, a block here, a block here. I've got m blocks, and so I have the partition function of one block and then it's raised to the nth power. And these are this is when v is equal to 0, then we have m non-interacting blocks. And so the partition function factorizes into the partition function for one block raised to the nth power. Okay, so let me just spend one more minute computing that. So what is z naught of k? It's the partition function for three spins. So I've got 3 spins, S1, S2, and S3, and then it is in the Hamiltonian is S1, S2 plus S2, S3 plus S3, S1, and these are all in the same block I. And I have these variables have to be plus or minus 1. And so if I have Si is equal to plus 1, well, then I can go back here where I've listed for Si is plus 1 all the 4 terms that contribute to that. So then I have to compute the S1i, S2i, S3i. So they're going to be these configurations. I'm going to sum over those. And so if I plug those values into z naught of k, Si equals plus 1, I get z naught of k is 3 e to the minus k plus e to the 3k. And you can see where they come from. This e to the 3k comes from this configuration. And then these three e to the minus k's are these three, 1, 2, 3. And if you put those values into up here, then you will see you get 3e to the minus k. And so that's the value when SI is +1. Okay, so I'm going to finish here, but I'm going to give you some homework. Okay, homework. Before next time, calculate Z0 of k for SI is equal to -1. Okay, this will take you 5 seconds. Okay, but I want you to do it, and I want you to do it without looking at my notes so that you know exactly what you're doing. Okay, so I'm going to finish now. So I'll take your question outside. I'm going to finish Zoom, and I'm going to, let's see, stop the recording.